Hi everyone. Today we have Zeyong with us. Zeyong is currently PhD student at CQT working with Divesh. He primarily works on lattice-based crypto, and today he's going to talk about his recent work. Oh wow, the title is too long. Maybe Zeyong, maybe you would like to continue from here on.
Okay.
Yeah.
So hi, good afternoon. This work this is a recent work that gives a 2 to the n over 2 time algorithm for approximating the shortest vector problem and the Hermite SVP problem to within square root n vector. And it's the joint work with Professor Divesh and Professor Noah. And a quick outlines for this presentation. So I'll start with some basic background information. And then we will look into the 2 to the n over 2 time algorithm from the previous work that was less powerful. And then we'll see what's the improvement in our algorithm. So first of all, the definition of a lattice. A lattice is this set of linear combinations with integer coefficients of some linearly independent basis vectors. And over here, I have a very simple two-dimensional lattice. Next, some notations that are related to the lattice. So we use lambda1 to denote the length of the shortest non-zero vector in the lattice L. And we use this to denote the set of cosets of the lattice over some sublattice L prime. And each of the cosets can be denoted as L prime plus C for some vector C in L. Next, we use this to denote the determinant of the lattice L. And more oftenly, I will be talking about the normalized determinant, which will show up in the next slide. The problems that we are interested in, the first one is the approximate shortest vector problem. Essentially, it says that given a lattice, we want to find a lattice vector that is non-zero and whose length is upper bounded by gamma times the shortest vector length. And similarly, for the approximate Hermite shortest vector problem, given a lattice, we want a non-zero lattice vector whose length is bounded by the approximation factor gamma times the normalized determinant, the determinant raised to 1 over n. Over here, we assume that the lattice has full rank, so its rank is equals to the dimension is n. And a quick remark, we know that there exists lattice such that the shortest vector, it's some constant times square root n times the normalized determinant. Therefore, for the gamma HSVP, the best approximation factor that we can hope for is some constant times square root n. So in this sense, our work in fact achieves the best possible approximation factor with some hidden polylog factor. Okay, so essentially, all these problems are saying that we want lattice vectors that are simultaneously short and non-zero. And another important component for this is the discrete Gaussian distribution. So it's the distribution defined over the lattice L, divide any lattice L, such that is essentially saying that the probability of seeing some lattice vector is proportional to this Gaussian mass. So by drawing the analogy to the continuous Gaussian distribution. And it also has a parameter S associated with it. For now, you can think of it as somewhat similar to the standard deviation in the continuous Gaussian distribution. And here is a nice illustration on how the discrete Gaussian distribution look like on the two-dimensional lattice Z square with parameter S when S is relatively large and when S is relatively small. And some other related stuff of the discrete Gaussian distribution. For each of the lattice L, there is a associated value, we call it the smoothing parameter. So it has a fairly technical mathematical definition, but the high level idea is that if a lattice has a small smoothing parameter, it means that that is a smooth lattice. And by smooth, it means that it's fairly dense in all directions. That's very loosely speaking. And secondly, for this parameter S, that it's above some poly n times the smoothing parameter, we know how to efficiently sample from the discrete Gaussian distribution. By efficient, it means that in polynomial time. And next, when S is above the smoothing parameter, then the discrete Gaussian distribution would behave nicely like a continuous Gaussian. So actually, this can be slightly illustrated in the two diagrams. So when S is like kind of large, it's the diagram is like fairly smooth, looks pretty much continuous. And when S gets small, it starts to look more discrete. And next, for some appropriately chosen small s, it's going to output the discrete Gaussian distribution is going to output some short vectors with some nice guarantee. And that's also how they find the shortest vector or approximate shortest vector in the previous work. And lastly, which is more relevant in this work, it gives us a way to upper bound the probability that the sampled vector is 0. So remember, from the previous slide, we want vectors that are both short and non-zero. So here gives us a way to upper bound the probability that it's 0. And here it's the final results of what our algorithm manages to do. So basically for square root n, for the approximation factor being square root n, we improves on previous works for both SVP and HSVP. And also for larger approximation factors, typically when c is larger than 1 for n to the power of c, we also make improvements via the basis reduction algorithm. And I'll talk a little bit more about this basis reduction algorithm towards the end of the presentation. Okay, next let's look at the 2 to the n over 2 time algorithm, a very similar algorithm from previous work that was less powerful. Okay, one of the key steps in that algorithm, I call that sieving by coset, works as follows. So suppose that we start with a list of vectors, x1, x2, blah, 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 from the lattice L1, and they follow the discrete Gaussian distribution with the parameter S. And what we do, consider some sublattice. Actually, it has to be a nicely chosen sublattice, L2, of index 2 to the n over 2 plus small o of n. The index basically says that there are this many cosets in L1 over L2. And we group the vectors based on the cosets they fall into. And for vectors that are from the same coset, we just greedily pair them and add them together. And because xj and xk, they are from the same coset in L1 over L2, we guarantee that this yi that we receive has to fall into L2. And the next step was to do some rejection sampling to carefully throw away some of the yi's that we have so that they are able to control the output distribution to be nicely the discrete Gaussian with over the lattice L2, and the parameter S would increase by a factor of square root 2. And a quick remark on the running time. So the running time was 2 to the n over 2 plus on, because there are this many cosets. So we need at least this many vectors so that we have enough vectors. We can guarantee that there are enough vectors to pair, and so that we can, the algorithm is able to proceed, because we are going to, in fact, repeat this process for some for some log n times. So we have to have this many vectors to start with so that we can continue. So this is a simple bound on the running time. And the limitation on this previous sieving by coset step is that the rejection sampling, the very last step where we throw away some of the vectors, it stops when this parameter S reaches around the smoothing parameter of L2. So remember, we mentioned before that when S is above the smoothing parameter, the distribution it's nice and it looks like a continuous Gaussian, which allows us to do a lot more things, including this rejection sampling step. And once S drops below the smoothing parameter, in fact, drops below square root 2 times the smoothing parameter, that nice property is gone and we are unable to proceed with the rejection sampling. So in their algorithm, they stopped there. And one more thing, why was this somewhat magic number 2 to the n over 2 plus small o of n? So this is one way to see what is actually happening. So if we look at what is going on, we are pairing vectors and adding them together. So the lengths of the vectors are growing. And by how much? If we ignore the rejection sampling and some other technicalities, we have the expected squared norm of the summed vector is, if we open up the square, with the expectation of xi squared plus the inner product term and plus the expectation of xj squared, which is 2 times the expectation of the squared norm of the vectors that we start with. Because this term is going to go away simply because xi is going to be distributed the same as minus xi. So the expectation of this is the same as the expectation of minus xi dot xj, which has to be 0. So in this sense, in one step, the squared norm grows by a factor of 2. So the norm goes by, roughly speaking, a factor of square root 2. So in 2 steps, the squared norm grows by a factor of 2. And at the same time, the lattice are getting sparser. So remember, the L2 is a sublattice of L1. So L2 is sparser than L1. And we want to make sure that the lattice are getting sparser faster than how the vector length gets longer. In this sense, we want to make sure that after 2 steps, the L3 is a sublattice of 2L1. So while the vector lengths double, we want to make sure that the lattice is getting sparser faster than doubling. And this straight away implies that the index in each step has to be strictly above 2 to the n over 2. And next, what happens in our algorithm? The very first step is that we don't want to do this rejection sampling. And to do so, we no longer can control the distribution to be exactly nicely discrete Gaussian. So we kind of have a looser definition of the distribution that we have. So we just ask them to follow approximately a mixture of discrete Gaussian with some target sublattice L prime. So a definition on this mixture of discrete Gaussian, a simplified version. So it just says that if we have this target sublattice L prime, and again a parameter S, then conditioning on this vector falls into this particular coset, the distribution has to be proportional to the Gaussian weight. So now we are conditioning on the coset that it falls into, and the cosets themselves might have some funny distribution, but we don't care about that anymore. So we have a bit more flexibility. And again, there is this guarantee that the parameter S has to be, in fact, above the smoothing parameter of this target sublattice L prime for the whole thing to work. Then again, we pair and add the vectors based on the cosets they fall into. And one key component here is that this pairing, we have a coset, we have a sublattice L2. It doesn't have to be the same sublattice L prime that we use here in the definition of the mixture of discrete Gaussian. And this is going to play an important role later on. And then after some calculation, we can show that the output vectors is going to follow approximately a mixture of discrete Gaussian with the same target sublattice and with the parameter increased by a factor of square root 2. So the next step, again, the algorithm, the sieving step in the previous slide, it's still limited by this smoothing parameter of the sublattice L prime. So again, we still need to have the guarantee that the parameter S has to be above the smoothing parameter. But the key catch here is that L prime only show up in the analysis. In the actual running of the algorithm, we don't need to know what L prime is exactly. So it suffices to show that there exists some nice L prime with a small smoothing parameter for the purpose of our analysis. And that's exactly what we did. So for the case where for SVP, we show that there exists some sublattice whose smoothing parameter is roughly lambda 1. And this is simply the one-dimensional sublattice spanned by the shortest vector. And for the HSVP case, we can show a somewhat similar bound on the existence of some sublattice whose smoothing parameter it's some factor times the normalized determinant. And this follows from a simple application of the reverse Minkowski theorem. And this is also like one of the algorithmic application of this reverse Minkowski theorem. Okay, so we have all the components that we need. So towards the end, the algorithm typically ends with a list of vectors from the lattice L. And this list of vectors follows approximately a mixture of discrete Gaussian with the target sublattice L prime, which we have shown to exist from the previous slide. And the parameter S that is around the smoothing parameter. That's where the algorithm have to stop. And to show that the vectors we get are, most of them are non-zero, we use the fact that they comes from a mixture of discrete Gaussian. So it has to, and so we get a upper bound on the on the probability of it being 0 from the discrete Gaussian. And at the same time, we carefully control the expected square norm of these vectors. And we can show that they have expected square norm around ns squared. So then we can use standard concentration inequalities, in which case we use Azuma's inequality to show that there are short vectors among this list of vectors. And that's all the ingredients we need. Okay, then let's talk a bit about this basis reduction. So basis reduction are algorithms that solves approximate SVP and HSVP by reducing the problem to gamma prime HSVP or SVP of lower ranks. And in particular, HSVP plays an important role in basis reduction algorithms. So in order to solve a large instance of SVP or HSVP, we solve a number of smaller instances, and HSVP is an important role. It plays an important role in the sense that it's the key ingredient that combines these smaller instances. And before this work, as far as we know, we typically use a gamma SVP algorithm to solve gamma square root n HSVP. So we lose a factor of square root n here. And in this work, we have an algorithm that solves HSVP directly. Thereby, we are able to improve the performance of these basis reduction algorithms. Okay, some of the open problems. The first one is that can our algorithm achieve a vector approximation factor? So there's no reason why its approximation factor has to stop at square root n. But in our analysis, we are unable to push it further. But we believe that it can perhaps do better, but to show that we need a completely different analysis. And secondly, the second question would be, is there a more concrete relationship between SVP and HSVP? So this algorithm solves both of them simultaneously to within approximately the same approximation factor. Both of them achieves the approximation factor of square root n times polylog n. And on the other hand, there are reductions from SVP to HSVP and from HSVP to SVP, but these reductions does not preserve the approximation factor. And in this sense, it shows that we don't have a good enough understanding of the relationship between these two problems. Okay, wrapping up, what was the key techniques that makes our algorithm work? So we avoid rejection sampling by substituting the discrete Gaussian with this mixture of Gaussians. And I would like to just mention that this technique shows up first in this work, where they avoid the rejection sampling on the 2 to the n time algorithm for solving exact SVP. And the next step was to show that there exists some unknown smooth sublattice to be used as the target sublattice. And yep, here is all I have. Thank you for your time.
Thank you, Zeyong. Are there any questions to Zeyong? If not, let us all thank Zeyong for the short and nice introduction to his recent work. And thank you, Zeyong.
Thank you.